Here's a relatively straightforward dimensional analysis question, which if you're a first year aerospace engineering or mechanical or ship science or civil engineering student, then this is something that you'll most likely come across. And it might be something that looks scary when you look into the Buckingham Pi theorem and general dimensional analysis, but it makes quite a lot of sense when you understand that all you're actually doing is just combining the different variables into their non-dimensional form. Okay? So this is done for the same reason why we have something like Reynolds number, right? So Reynolds number is the ratio of what we call inertial forces over viscous forces, right? Although we're not actually dealing with forces, because this is not a force and this is not a force either, but this specific combination of variables, first of all, is dimensionless, so this has no units. And it also tells you something about the flow, usually whether it's laminar or turbulent. And this is used, the reason why we use non-dimensional parameters like Reynolds number or lift coefficient or drag coefficient and so on, or Mach number, is so that we have a way to compare an experiment done in the wind tunnel with the real life application, which is the actual, let's say, aircraft. Okay, so dynamic similarity means that your experiment and your real life application will use the same Reynolds number. And if you know the two Reynolds numbers are the same, then you can find things like, okay, what speed should my aircraft fly at? Or rather, what speed should I do the testing in the wind tunnel? Okay, or what should be the size of the model? That's the diameter, for example, or the chord length or anything like that. So yeah, that's the basic idea. So let's look at this simple example, which combines, so here's the problem. The velocity of sound, A, of a gas varies with pressure and density. And show by dimensional reasoning that the proper form must be A equals to some constant times P over rho to the power 1 over 2. So let's get rid of this for a second and let's start analyzing this. So the first thing we do is we look at how many variables we have. So we have three variables. We have A, we have pressure, and we have density. And we write each of them one after the other. And then the next thing I would do is write the units for each of them. So speed of sound is a speed technically, so it's measured in meters per second. But instead of using meters, second, and so on, because some people might use imperial units, for example, which I don't particularly recommend. But rather than looking at the SI units themselves, instead of meters, I'm gonna replace meters with L for length. So this is saying that meters are measuring a length, okay, in the same way that kg, kilograms, are measuring mass. Okay, don't confuse this one with this one. Okay, this is meter, this stands for mass. And second, I'm gonna use T for time. Okay, so instead of meter per second, I'm gonna change this to L over T, or rather I'm gonna change this into L T to the power minus 1. And then I'll do the same thing with pressure. So what's pressure? Well, we'll start from the definition of pressure in a way. So pressure is Newton per meter squared. Okay, and then what is Newton? Well, Newton is kilogram times, so mass times acceleration, kilogram meter per second squared over meter squared, like this. So this turns out to be, we can cancel out this with this, and we're gonna get kg over ms squared, or we can turn this into, let's put a rectangle around those. So kg is mass, m is L to the minus 1, and then T to the minus 2. Okay, and density is kilogram per meter cubed. So kilogram is mass, meter cubed, this is going to be L to the minus 3. Okay, so that's what we have. Let me rewrite everything again on here. So I'm going to say that A is going to be, I'm just going to put those sharp brackets around just to show that just to show what the units are. So we have this for A. Now A is not acceleration, that's the speed of sound in this case. Pressure is, what did we say? We said it's equal to this. So it's m L to the minus 1 T to the minus 2, and then rho, the density, is going to be equal to m L to the minus 3. Okay, and if you want, you can number those like this. So we have three variables. Okay, right. So we have three variables, and if we have three variables, then the next thing to do is to count how many independent units we have. Okay, so how many independent units? How many independent units do we have? We have L, we have T, and we have M. So we have three, let's say, units. Okay, then what we do is we subtract the number of units from the number of variables. So we're going to do 3 minus 3, and of course we end up with 0. Now in this case, what this tells us is that we have 0 pi groups. So what this actually tells us, and you'll see this again in the next example, but this tells us that all variables, so if we end up with 0 pi groups, it means all variables are what we call repeated variables. Repeated variables. So what this actually means, in a more intuitive way of explaining, it means that all of the variables, so all variables can be combined into a non-dimensional variable. Like this. Okay? So let's try to do just that. So I'm going to try to combine the speed of sound, the pressure, and the density into something that is non-dimensional. And the way to do that is as follows. So I'm going to take A and I'm going to raise it to the power of X, and I'm going to multiply that with pressure, and I'm going to raise it to the power of Y, and then multiply by density to the power of Z. So I want to have X, Y, and Z such that whatever comes out on the right hand side will have no units. Okay, so this will have, let's just write here, no units. So I'm going to replace A with the units of A. Okay, so for A we have length time to the minus 1 to the power x multiplied by, and then we have the pressure, which is m L to the minus 1 T to the minus 2 y, and then this is times ml to the minus 3, everything to the power z. So this one has no units, which means that on the right hand side I should end up with length to the power 0, right, which is 1, m to the power 0, t to the power 0. So those powers should combine so that everything cancels out and I will end up without any units. And that will tell us how we should group, or what should those powers be, so that we can group the three variables together to get something non-dimensional. So let's do some maths at this point. So I'm gonna expand all the brackets as follows. So the first bracket is gonna be L to the x, t to the minus x, times m to the y, L to the minus y, and then t to the minus 2y, times, and then we have m to the z and L to the minus 3z, and that's equal to L to the 0, m to the 0, t to the 0. Okay, so let's now separate and compare the powers on both sides. So we have, let's look at L first. So for L we have this, and this. So we have L appearing 3 times, and the result is going to be L to the x. L to the x times L to the minus y is going to be L to the power x minus y, and then this is going to be minus 3z. And then I'll do the same thing with mass. So mass is going to be just y plus z, right? Because mass only appears here and here. And time appears here and here. So time is going to be raised to the power minus x minus 2y. And this is going to be L to the 0, M to the 0, T to the 0. So the only thing left to do is literally just to say that this, for this to be equal to the right hand side, it means that has to equal to this 0, then this one has to equal to this 0, and this one has to equal to this 0. Okay, so let's write them as such. So we have x minus y minus 3z is equal to 0. Then we have y plus z equals to 0. And then we have minus x minus 2y is equal to 0. Okay, so this is what we have. So let's try to see how we can solve this, first of all. Now, you'll notice that at this point, this is actually a homogeneous system. So it's a homogeneous system, which means that the only way to get solutions out of this is if at least two equations are dependent. So let's start with this and let's write z in terms of y. So this becomes z is equal to minus y. Okay, and then if I take that and if I, let's say, place that in here, in the first equation, what I'll get is x minus y minus 3, and instead of z I'll write minus y again, equals 0. So this gives me x minus y plus 3y is equal to 0. So x plus 2y is equal to 0. And as you'll see, this equation is the same as this equation. So if you multiply this by minus 1, you'll get the final equation, which means that those two are not actually independent. You can obtain one from the other by just, in this case, multiplying by minus 1. So the question is, what do we do at this point? So at this point, what I would do is I would write y in terms of x. So x plus 2y is equal to 0, meaning that 2y is equal to minus x, which means that y is equal to minus x over 2. Like that. Okay? So we have y is equal to minus x over 2, which means that z is going to be equal to x over 2. Right, from here. So, because z is equal to minus y. So, let's see how that makes sense, or what does this actually mean. So, we have that the power of a, which is here, so we have this to be x, then let's write it here. So we have that is x, then the next parameter is p, so p, and that is to the power minus x over 2 times, and then we have, I think, rho. Yes, we have rho to the power x over 2. And this is, essentially, this is going to be equal to a constant. Because if we choose the powers in this way, we're going to end up with something that has no units. We're going to end up with a constant, which, let's call this constant c for now. Okay, so what I'll then do is I will write this in terms of a specific value of x, because we're close to the final answer, and at this point what you should do is just give x a value that makes sense. So what they're actually asking is show that a is going to be equal to a constant times that. So if we take x is equal to 1, then what we end up with is a to the 1 times p to the minus 2 times rho to the 1/2 is equal to this constant c. So a times, I can combine those two together as follows. So this is going to be rho over p to the 1/2, and that is equal to c. And if I cross multiply, I'll get that a is equal to p over rho to the 1/2 times c. And this actually looks like what they're asking for. Now, technically, your x can be anything, because if you make x 2 or 3 or 4 or 1.5 or anything like that, this quantity here will still have no units, okay? But the one form of this equation that we're interested in is the one that looks like what they have here. And as you can see, this one has an a to the power 1. So we make the power of a1, which means in this case we make x1. And if x is 1, this is minus a half, this is a half, and we end up with this, which is actually a true expression. So this tells you that the speed of sound in air is or depends on the ratio between pressure and density to the power 1 over 2. Or more specifically, it says that A is proportional to the square root of P over rho. Okay, and actually another way to write this is that the speed of sound is equal to the square root of gamma RT. Okay, and you can go from here to here, so you can go between those two formulas using the ideal gas law. Okay, and this is actually what is, I think this is the more common way of writing, of expressing the speed of sound, but this one works as well. So this is what we showed in this case, that the speed of sound in air is proportional to the square root of pressure to air pressure over air density. And we did that using some dimensional analysis. And that's the end of the question.